Hi, welcome to the Signal Path. In this episode, we're going to do another tutorial. Over the years, I've done a lot of tutorials on some fundamental concepts, things like linearity, equalization, various communication networks, data converters, and so on. So today we're going to talk about phase noise. Phase noise is one of those ideas that you have to fully understand if you want to design pretty much any system, because it's an important idea, whether it's a wireless, optical, wireline, or radar system. So this is a very important concept. Aside from that, we're going to talk about the theory, the measurement techniques, and how these measurements need to be set up, some of the things that can go wrong, how the instruments work, but also we're going to take a look at some really high-end instrumentation that can do cross-correlation and do some fancy measurements to eliminate the phase noise of the instrument itself. So these are pretty advanced topics, and it gets more and more complicated as the video goes on. Hopefully you will find most of it useful. Let me know in the comment section what you think, because these are pretty hard to put together, but I don't think there is a video out there that covers this much stuff in one place, and hopefully it will give you a nice end-to-end understanding of how phase noise works. So let's get started. So first we have to learn about what phase noise is from a theoretical point of view. And please bear with me through this presentation, because it's important for us to understand what phase noise is, so that when we do measurements, we can correlate that with the theory and better understand what the instruments are actually doing. So not only are we going to talk about the idea of phase noise and its mathematical representation, but we're also going to talk about how instruments can measure phase noise to give you a complete understanding from end to end. And of course, we'll do teardowns and measurements to complete the picture. So I was making some slides and I came across this particular one right here, and I was very happy to find this Keysight slide deck by Bob Nelson, which goes through the details here, which is perfect because it saves me quite a bit of time. So thank you, Bob, for making this publicly available. So let's dive right into it and see what it's all about. So first, let's make sure we don't confuse the stability of a source with its phase noise. So stability typically deals with how stable a source is across a long period of time. This could be days, months, or even years. Now, this is still a very important parameter, and I've talked about this in many different ways. For example, if you have an oven-controlled crystal reference source inside a spectrum analyzer, that source is going to drift slowly as time passes. That drift is going to give you the absolute accuracy of the spectrum analyzer. So if the spectrum analyzer tells you that you're measuring a signal that's 2 gigahertz, it knows that it's 2 gigahertz because it's comparing it ultimately with its own reference. That's the absolute reference it has. Things like Allen variance or parts per million per year, for example, are the kind of terminology used to describe how stable a source is. We don't typically consider this phase noise because it is such a long-term effect. Nonetheless, very important for defining absolute accuracy. Even for wireless transmitters, this can be pretty important. So if you have a crystal that ultimately sets the local oscillator of the wireless transmitter, that's the frequency you're going to be transmitting over the air. And if it drifts too much, you could even go outside of the range which you're allowed to transmit. There's a whole bunch of discussions around that, which we may do at a different video. But the short-term frequency stability, that's the part we're interested in, because that defines how the phase and the frequency of a source changes on a short term across time. So you can imagine that if you have fluctuation in frequency and fluctuation in phase, then you're going to have some uncertainty with regards to what that source is doing. And that can be over short term in the millisecond, microsecond, or during 1 second periods. So we're going to take a look and see how does that affect the spectrum of a signal, and how can we measure that, and how does that ultimately define what the phase noise of a reference signal is. So let's first look at an ideal sinusoid. So here's an ideal sinusoid here, and it can be defined across time as a sine of 2 pi ft. This is pretty straightforward. It's a sinusoid with an amplitude a0 and a frequency of f0. So this sinusoid is going to have only a single frequency content, and of course that frequency content is at f0. If I were to draw that across time, this is what I would get. Although I have to say this is a pretty bad sinusoid, because the top of it is not round, it's flat, which means that this is going to have harmonics associated with it. And I've made videos about how these harmonics show up and how they have intermodulation products with other sinusoids that are present in the system, and we've talked about that in different videos. But for the purposes of this one, let's assume this is a perfect sinusoid. If I were to take the Fourier transform of this sinusoid, I would get a single tone. It's a pure tone, and this is what we would want. This is how an ideal signal source at frequency f0 would operate. But of course, everything is not ideal, and we're going to have various types of imperfections. The very first imperfection is going to be some amplitude noise. And that amplitude noise is going to add to the original amplitude that you want. Of course, this E of t is going to have to be much smaller than A0. Otherwise, the dominant tone in the signal is not going to be the sinusoid you want anyway. But E of t itself is a time-varying signal. and it could be random, it could be itself made of multiple tones. Depending on what kind of noise the circuit has, it's going to be completely depending on that. So EFT can even be amplitude modulation and can be used to transmit wireless data. That's how AM radio works. So EFT is noise, and it's of course a function of time, so let's assume that's there. That means that if I were to plot the sinusoid, now it's going to have some noise associated with it, and that's going to change and modulate the amplitude of the sinusoid across time. At the same time, I can have the term phi of t in here, and that is going to modulate the phase of the signal. That sine of 2 pi ft plus phi is now going to have its phase wiggle and move around depending on how phi of t is. The phi of t itself is across time. It can have its own very complex waveform associated with it. So how does this relate to phase noise? Well, first of all, here's phi of t, just in case you didn't notice it. This is going to move the zero crossing of the sinusoid. So how does this show up in the frequency domain? Well, think about it. First of all, this E of t is multiplied by the sinusoid, which means that this frequency is going to shift around and it's going to appear around the f0 frequency. It's essentially up converted to the frequency f because it's multiplied by the sinusoid, which means that the frequency content of E of t is going to appear near f0. And that's a problem because it's going to show up right close to the frequency tone that you're interested in. What about phi of t? Well, you have a sine of x plus y. And if you expand that, you're going to get the product of sine and cosine of the two terms inside. That means that that itself is going to get up converted also around the frequency f0. This means that the frequency f0 tone that used to be in the middle, like this, as we saw before, is going to now have a whole bunch of frequency content right near it. And this frequency content is going to be symmetric around f0 because both of them are directly multiplied with the sine of 2 pi f, so it's going to show up on the upper and the lower sideband at the same time. And this is what you would expect if you were to measure a signal source with a very clean spectrum analyzer. You would see what is known as the skirts around the carrier frequency. So now that we can see that both amplitude variation, so AM noise, and phase variation, PM noise, will show up in the spectrum near the frequency f0. And that is the kind of thing we have to look for when we're going to measure phase noise. But of course, this is just how it looks. Well, how do we model it and how do we measure it? And what's a good way of giving this some mathematical representation? So we established that both AM and PM modulation is going to show up symmetrically on both sides of the carrier frequency f0. This means that when we talk about phase noise, it's sufficient to really measure the single sideband frequency content. There's no reason to look at the double sideband. So that's enough for us to characterize phase noise. So how do we do it? Well, let's establish some numbers and some methodology for measuring it before we talk about how it is characterized mathematically further. So let's say you have a frequency f0 in the middle. That's your tone. That's the tone that you want to be as ideal as possible. As you have more AM and PM noise on it, these skirts are going to move up, which means there is going to be more power away from the carrier, which means the phase noise is worse. That's what you don't want. Now keep in mind that this phase noise is going to drop as you go further from the carrier, and that's because of Bessel functions, and we'll talk about that in just a second. But for the purposes right now, it means that the lower these skirts are, the better. And if they go all the way to minus infinity, you're going to get back to the perfect sinusoid. So how do we measure phase noise, and so I can give it a number? Well, we have a tone over here. That tone is going to have some amplitude. Let's say it's 0 dBm. Okay, it's a 0 dBm sinusoid. And then we move away from the carrier by some offset. So we have to define what that offset is. Normally for phase noise is measured across many different offsets. So this offset can be 1 Hz, 100 Hz, a kilohertz, a gigahertz. It doesn't matter. That offset has to be mentioned because it tells you how far away you've moved from the carrier when you want to measure phase noise. Then we take a 1 Hz bandwidth and we measure how much power is in a 1 Hz bandwidth away from the carrier. So if this carrier offset is, let's say, a kilohertz, you say that I measured, let's say, minus 100 dBm at a 1 kilohertz offset from the carrier. Then you compare that to the main tone, and that would give you a dBc value. And since in a 1 Hz bandwidth, that would be in dBc per hertz. So for example, I can say that my sinusoid, which is at 1 gigahertz, has a phase noise of minus 100 dBc per hertz at a 1 kilohertz offset. So that means that this number is mentioned, this number over here compared to the amplitude over here is mentioned, and of course the carrier is mentioned. And that's what you get in this equation here. So whenever you see phase noise, you have to have offset mentioned, the actual frequency, and of course the dBc per hertz value mentioned. That would tell people how good this source is. So if I say that my phase noise is minus infinity dBc per hertz, that would be an ideal sinusoid. And if I say it's minus 20 dBc per hertz at, let's say, a 1 kilohertz offset, that would be a pretty terrible source. So now we have to look and see why these skirts fall like this, and how can we relate that to the actual jitter or actual phase noise that you see in the signal. So in practice, when we talk about phase noise, one of two things can happen. You either know how much phase modulation your signal is experiencing, and you want to calculate what the phase noise would look like. Or you measure the phase noise and you want to find out how much phase modulation is being applied. Both of those are useful. Now, if you know anything about phase modulation, you know that you can use Bessel functions to calculate the frequency content of a phase modulated signal. And you can see the shape of these Bessel functions as you move away are going to drop just like the phase noise would drop in the examples we've been talking about. So if I have this information, I can use this and move backwards and find out how much phase modulation I have in the time domain. This can be pretty powerful because often we measure something and we want to find out how much phase modulation we have. And of course, this goes both ways, just like a Fourier transform can go back and forth between time and frequency domain. So you can look at the details of this. I won't go into too much of it. I just want to get the fundamental point across. So here you can see that if you have a carrier and we modulate that carrier with a phase modulation of a small amplitude, you will get two tones on each side. That would happen if the phase modulation itself was sinusoidal. And you can find out the relative power between this peak signal and the tone you see away from the carrier using this equation, which is exactly what we want. That's what phase noise is the relative power of the fundamental tone to the skirts or to a tone away from the carrier. So you can see that the relationship is very straightforward. And you can get the RMS value of the phase modulation by looking at the relative of those two powers. That would allow you to go from the frequency into the time domain. We can take that a step further and define an equation to go the other way. So now we have this equation over here, which you will see over and over again whenever phase noise is being discussed. This tells you what the frequency content of the phase noise away from the carrier is if you know the RMS value of the phase modulation. You divide that by the bandwidth. That's how you get the dBc per hertz, and that will give you L of f. The reason this is a powerful equation is because the phi RMS can be any waveform. It can have any spectral content, and that will change the shape of the L of f on the side. If the phase modulation is a tone, well, L of f is going to be a tone itself. If it's going to be a noise signal, it's going to be a totally different shape. And that's one of the ways it's used. So we can use this to calculate phase noise, and we can take that a step further, and we can say, what if I know the phase noise? What if I've measured the phase noise and I want to find out what the RMS of the phase modulation is in radians? Well, you can take the phase noise that you measure, which we're going to do using the instruments, and you can integrate between two frequencies, start and stop. So you can say, I start from a 1 kilohertz offset to a 100 megahertz offset, and you integrate that, and then that will give you the RMS value of the phase modulation in radians. This is done all the time to characterize different oscillators and their performances in the time domain. So I can tell you that, I have an oscillator and it has an RMS phase noise of, let's say, 0.001 radians. That can be a number, and you can translate that back on what the frequency domain would look like. Now that brings us to the next topic, which is jitter. The difference between jitter and phase noise has only to do with the fact that jitter is thought about in seconds as opposed to in radians. Now, you don't typically hear jitter when people talk about phase noise. Jitter is often reserved for data communication on data that comes through, defining how the edge transition of the data changes over time. I'm going to do a separate video on jitter once I have some instrument that I'm waiting for. Then we can talk exactly about how jitter works and how you can decompose jitter, and that's a whole other topic itself. Nonetheless, you can calculate the jitter in seconds by taking the RMS value and multiplying it by the period of the frequency. So it's very simple. You just divide the RMS value you got from the integration by 2 pi fc. So you can see that as frequency grows, the jitter will actually go down if the phi RMS is kept constant. So that's all I wanted to say about phase noise, just to give you an idea. So let's go ahead and do every single one of these things we talked about. Let's do some phase modulation, look at how it looks like in the spectrum domain, Let's measure some oscillators, and then I want to show you a really cool piece of instrumentation that can measure phase noise in a really incredible way to go super low phase noise measurements. So let's jump to that. So here's our basic setup for understanding AM/PM modulation and looking at the differences between the frequency and time domain so we can compare it with the theory we just saw. Here on the left I have the Tektronix AFG 31000 series. We're going to use this to generate our signal, and the Tektronix 5 series MSO, which allows us to analyze them. We have channel 1 of the ARB connected directly to channel 1 of the scope, same with channel 2. The reason we do this is because we can trigger on channel 2, and that allows us to not trigger on the channel we want to look at the signal in the time domain, so we don't have a trigger line in the middle of the screen that allows us to look at the signal across the entire screen and see how AM, PM, and FM modulation actually looks like. At the same time, we have spectrum view, which is a capability of the MSO. We can look at the frequency and time domain side by side. Here on the ARB, I can apply various types of modulation, and therefore we can do a direct comparison very quickly. So let's go ahead and do a screen capture on the oscilloscope, and that way we can take a close look at the waveforms. And here's the screen of the MSO5. At the very top we have the spectrum view. Center frequency is 100 MHz and the span is 20 MHz. Resolution bandwidth is 2 kHz. And at the bottom we have the time domain view, 10 nanoseconds per division, and we have a vertical spacing of 100 millivolts. So this looks very nice. Now right now the ARB is disabled, but even though it's disabled we still see a tone here at 100 MHz. And the reason is because the output of the ARB is disabled using a mechanical relay. The ARB itself is internally running, the DAC is running and continuously producing a signal. By not disabling the DAC completely, you can keep phase coherence between enabling and disabling the output, and there are some advantages with that. But of course you're going to see the leakage through the relay now. That's the isolation limitation of the relay. But the signal is tiny. It's minus 66 dBm or so, and the reason we can capture it is because the front end of the oscilloscope is so low noise and the vertical resolution of the ADC is very high, and that's why we can capture that. It's pretty impressive to be able to do this. So let's go ahead and enable the tone and see what the tone looks like. Here's our tone. Looks nice. You can see it's very sinusoidal. Now even though this tone is supposed to be ideal, you can already see some tones and some various other harmonics around. And the reason is because of the internal operation of the DAC, and there's some mixing terms and some clock divisions and some switching noise and so on, which will always show up. But these are again very small. The output amplitude of this sinusoid is 0 dBm roughly, and the difference between these tones is over 70 dBm. So it's pretty impressive to see them at all. Okay, that looks good. So now we can go ahead and add AM modulation. So let's go ahead and do that. We're going to add our AM modulation. Here it is. Here's our AM modulation. This is a 1 MHz modulated signal, and the depth of the AM modulation is 25%. So you can see, if you look at the top and the bottom of the sinusoid, very clearly we have some smearing, or we can clearly see that there is noise added. Now this is most prominent at the peak of the signal. That's because that's where the signal spends most of its time gradually going across time, whereas the slope is the highest at the zero crossing. So you don't see it much at the zero crossing. It's prominent at the top and the bottom. Now in the frequency domain, you can see a tone on the left and the right, very symmetric on the upper and lower sideband, and you don't see the Bessel function tones because this is an AM modulation. But remember, for small modulation, AM and PM would be indistinguishable. That's why carrier removal is so key. The only difference between them is actually in the phase domain. You cannot see it in the amplitude domain like we see in the spectrum there. So let's go ahead and now switch this from AM modulation to PM modulation. So we can do that as well. So here is our phase modulation. There it is. Now this phase modulation is also 1 MHz and at 20 degrees, and you can clearly see now we have a zero crossing that is blurred out because every time the signal is captured there is high persistence here. You can see it traveling back and forth by about 10 degrees. In the spectrum domain you can see now the Bessel functions very clearly. But if I reduce the depth of the modulation from 20 degrees, let's say, to 5 degrees, you can see that the Bessel functions begin to degrade very quickly, and eventually if this tone disappears, AM and PM become indistinguishable. So let's go back and put this at 20 degrees. Now this is a sinusoidal modulation, which why we see the nice Bessel functions there, but I can change that from a sinusoid to a different type of modulation. Instead of sinusoid we can do square. So what do you expect to see? Well, you will not see this clear smearing of the zero crossing with high persistence there, because with a rectangular modulation, you will only have two states. So let's go ahead and try that. Here's a square wave, and if you wait long enough, there it is. You can see very clearly two edges, and that's because it's either high or low on the square wave. Now look at the spectrum content. It's a mess of a lot of tones. That's because the square function itself has many tones. Now even though the square function doesn't have all the even and odd harmonics at the same time, you can see that the other tones are there, again due to the bezel. Now if I change that and do exactly the same thing on the AM modulation and switch the modulation from sine to square, those tones will be missing, again for the same reason I just explained. And now you can clearly see on the vertical axis the two edges. That's because this is AM modulation. So all of this matches theory very, very nicely. The only one left is FM modulation. So here's an FM modulation. This is a 1 megahertz modulated with a deviation of 10 kilohertz. Now we notice something interesting. First of all, we do see the two tones on each side. That's to be expected. But you can see that this waveform keeps moving. And the reason is because the ARP doesn't seem to be able to maintain a fundamentally fixed carrier of 100 megahertz. There seems to be some shift when it does FM modulation. This is most likely a bug in the firmware that I would have to report to tech so they can fix it. So the signal is moving back and forth at 10 kilohertz, but there is now a fixed offset, and that's why it drifts with respect to the other channel. If I go ahead and enable the other channel so you can just see what the other channel looks like, here's the other channel. So we're triggering on this one, and even though they're both supposed to be a center 100 megahertz, there's going to be some shift. So it doesn't go up and down by the same amount with FM modulation. So this is all really interesting and basically confirms everything we were talking about. Now we can go ahead and go even further and go back to our phase modulation, and instead of a square wave, let's do noise. So with the noise, now we're going to see a totally different spectral density here. So this power spectral density that you see, that's now actually phase noise, and what you see on the time domain represents a completely random phase noise. Now this has a sync shape to it that has to do with how the noise function is calculated inside the ARP. In reality, you won't have a sync-shaped noise function. You're going to have a totally different power spectral density. This is also an interesting artifact of how the ARP operates. But all of this matches theory very well. So now the question is, well, I'm going to talk about why we don't use oscilloscopes generally to measure phase noise, but then we're going to move on and use a spectrum analyzer. So why is it that people don't use oscilloscopes for measuring phase noise typically? Although people do use oscilloscopes for measuring jitter for data communication purposes, and that's for a whole other video. Well, the main reason is essentially dynamic range, because if you think about it, an oscilloscope is a real-time system. So if you want to find the phase noise, let's say on a 5 gigahertz signal, you'd have to sample that at quite a few times higher than 5 gigahertz and then capture a long stream of data, perform FFT, and then find out how much phase noise you have. Because the ADC has to run at a much higher sampling rate, its dynamic range, or its effective number of bits, is going to be quite a bit lower. Whereas you can easily use a 16-bit converter in a spectrum analyzer because you're looking at only the IF signal. Instead, you do down conversion with a sweep in order to be able to get the signal you're looking for. The second reason is because the ADC in this system would have to capture the carrier and the phase noise simultaneously, whereas in a spectrum analyzer, the carrier can be removed through pre-selectors and other techniques in order to not have the dynamic range of the analog to digital converter occupied by the carrier. Then you don't have to resolve a tiny power away from the carrier while simultaneously trying to digitize the carrier at the same time. So a spectrum analyzer is inherently quite a bit more powerful for that reason. Also, very small AM modulation and PM modulation, as I talked about earlier, are indistinguishable in the frequency domain without looking at the phase. And you could do that on the oscilloscope. You'd have to have some software, but carrier removal will have to happen no matter what in order to isolate PM from AM modulation. So there are quite a few reasons. That's why essentially people never use oscilloscopes except for subsampling oscilloscopes, which I've shown in other videos, which can be used for these purposes for other reasons, and they have a very high dynamic range. And when we get into the jitter video, we'll talk about that too. So now that we know this, let's go to a fairly high-end spectrum analyzer and do all of these things in there using a different source, and we can take a look at the softwares that enable phase noise measurement and how you can directly measure it on the screen of the spectrum analyzer. And then I want to show you the block diagram of a really advanced measurement system so we can see how that one works, and then we can do some really interesting experiments at the end. So let's go. So now let's go ahead and use a spectrum analyzer to measure phase noise. We're going to use the Keysight EXA at the very top. My MXA-B version is under repair and calibration, so we can't use that, but this has basically the same software. We can establish the performance the same way. And I'm going to have used 3 sources here to measure their phase noise, and we can look at the characteristic of these 3 different sources. We're going to use the tracking generator of the Siglent SV810X as one of our sources, then the portable ERA synthesizer, which I've reviewed also, as another one, and finally the Signal Hound PNCS1, which is a phase noise reference, exceptionally clean 1 gigahertz reference, and we're going to compare them directly on the EXA. So let's go ahead and zoom on that screen and see what these phase noise behaviors look like. Okay, here's a close-up of the screen, and I'm interested in measuring the differences in the phase noise between these 3 sources. Right now I have it hooked up to the Siglent SV810X, and it's set to 1 gigahertz with a power of about 0 dBm. So you can see some tones here, the second harmonics are there, some other spurious tones are being generated, but we're really only interested in looking at the tone by itself. So let's go and change the center frequency to a gigahertz. There's our tone. Let's change our span to 1 megahertz. So we're looking really close at the tone with the lower and the upper sideband on each side. We expect that to be symmetric, as we discussed from the theory as well. So let's go ahead and change the resolution bandwidth now, because the resolution bandwidth is very large. We don't really get a good insight on the shape of the skirts on each side. Let's go ahead down to, let's say, 30 hertz. There it is. And you can clearly see the shape of the phase noise. Now, the shape of this phase noise is a function of many things. And when I do the tutorial in the future about PLLs, about phase lock loops, we will be able to discuss and find out exactly what's going on. But for now, this is the shape. Now, I can do a peak search, and that tells me the carrier power. The carrier power is minus 1.3 dBm. That we need that, as if you recall from the theory, we need to compare the power of the carrier to the power in a 1 hertz bin away from the carrier at a particular offset. So we now know the carrier power. Let's say it's around 0 dBm, minus 1 dBm. Okay, well, I can move the marker. I can set the marker to a new location. Let's set it to, let's say, 100 kilohertz offset. Okay, so there is our marker right here. Now you cannot read this number, because this number just tells you the power measured at this point. This does not give you spectral density. So this is in dBm. You want it in dBm per hertz. But the instrument can actually give you that value, because we can change the marker function to give you noise density. So we go under marker functions, and we select marker noise. Now when you have marker noise, it will give you the value in dBm per hertz. So what it's doing is it is measuring how much power there is in a 1 hertz bin. So minus 99 dBm per hertz. Now we can no longer measure the peak. You can see it's quite a bit lower than it used to be, because the detector type has changed. So we have to remember that from the previous measurement when the marker noise was not active. It used to be about, let's say, minus 1. So if this is minus 1 and this is minus 99.6 dBm per hertz, the phase noise at a 100 kilohertz offset is minus 98 dBc per hertz. There it is. We just measured the phase noise of the SV810X. So now we want to compare it to another source. Well, in order for me to avoid going back and forth between the marker functions, I've already set all the sources to generate 0 dBm. So that's constant. Therefore, we can just look at how much power we have in a 1 hertz bin. We only have to look at this number when I switch the sources. So let me go ahead and switch the source. Let's go from the Siglent to the ERA synthesizer. Let's plug that in. And there it is. And check it out, it's quite a bit better, and it's in fact so close to the bottom of the screen, we're going to have to change the reference amplitude to minus 10. Now we have to be careful here, because this tone is still at full power. We have to make sure we don't saturate the instrument, but anyway, that's a separate point. So right over here, you can see now we're at minus 114 dBm per hertz. We are 14 dB better. That's a huge difference between the 2 sources in terms of the quality of the synthesizer. And of course, this is not quite a fair comparison, because the other one is the tracking generator, not really intended to have a very good phase noise, but nonetheless, we can see the difference is quite big. So there it is. Now we see that this guy is, first of all, the shape of the skirt is quite different, because the PLL characteristics are quite different. Nonetheless, we have quite a bit better. So now let's go from the ERA to my PNCS1, which is supposed to be the cleanest source I have in the lab. So we expect that to be much better. Let's go ahead and swap it. Disconnecting it from the ERA, connecting it directly to the PNCS1, and there it is. But wait a second, that doesn't look quite right. This is only a few dB better. This is minus 117 dB ampere hertz. This source is supposed to be considerably better at this offset. So what's going on? Well, first of all, the shape looks almost identical to the other source. So why is it that this is not so much better than the other one? Well, I'm going to let you think about that. But before that, let's go ahead and use the actual phase noise measurement software and see what that looks like. We can change the mode of the instrument to phase noise. Now in this mode, the new software is running in the background, of course. We can see it knows the carrier is at a gigahertz. But this is not the mode we want to work in. We want to change the display. We want to use actually, if I can figure out or remember how I change that. There you go. We want to do a log plot. Okay, so we're going to put this in continuous mode, and I'm going to change the settings. We're going to go from 100 hertz. Let's stop at 100 megahertz. There you go. So what the instrument is now doing is automatically plotting the phase noise at a given offset. So it starts at 100 hertz offset and goes all the way to 100 megahertz offset. So in this example, the carrier is actually sitting somewhere here, just outside of the screen. But you never want to look at that anyway, because the instrument is automatically measuring its power. So you don't have to worry about it. And it's doing AM rejection and all that, which we don't have to worry about when you're running this software. So this is now the shape of the phase noise. Now I can do a bunch of interesting things. I can do, for example, different types of detections. I can do averaging. Let me see. What did I want to do? Let's turn the averaging on first. I'm going to do this like this. So there you go. So it's going to give us a nice smooth curve. So what I can do is I can put a marker on there, and the marker is now going to tell me what is the offset. So the offset of 100 kilohertz, the phase noise is a minus 116.8 dBc per hertz, which is exactly what we were measuring when we did it manually ourselves by looking at the power of the carrier versus how much power we had in a 1 hertz pin at 100 kilohertz offset. So this number matches what we did. We were measuring minus 117. This is minus 116.9. It's about the same value. So another question was, well, why is this so much worse? And why is the PNCS1 not so much better than what we were expecting from the ERA? Well, the trick is that right now we are actually measuring the phase noise of this instrument. We are no longer measuring the phase noise of the PNCS1. The reason is because this guy's internal synthesizer is going to have its own phase noise added to whatever you're measuring. So as long as what you're measuring is significantly worse than this, at least twice worse than this, then you are measuring the source. But as soon as the source gets better than the instrument, now you're measuring the instrument. And that can be a pretty big trick to play on people if they are not familiar of how these instruments work. You'll be ending up measuring the EXA versus the source you're looking for. Now this software can do some other fancy things. For example, we can go ahead under marker functions and we can measure directly the RMS phase noise that we have as I described in the theory. So right now it's in degrees. I can press that and I can adjust the bands. Let's say that I want to find out what is the integrated jitter between two offsets as we described from the theory. Let's say we take the left one to be at 10 kilohertz and the right one to be, let's say, at 20 megahertz. Maybe I should change the left one to 1 kilohertz. There we go. So it's measuring the jitter from here to here, and it's giving us 106 millidegrees. And I can change the unit of that. Let's do it in seconds. 293 femtoseconds. So that's the jitter between these two bands integrated across the entire phase noise. Now I'm going to remove this, and I'm going to hook it back up to the Siglent SVA. You can see how much worse the Siglent SVA actually is. There we go. I'm going to restart that measurement. Take a look. 1.3 picoseconds. That's a huge difference, and that's to be expected because the phase noise was quite a bit worse. And if I go under the marker functions and put the marker back to 100 kilohertz offset, you can see that we're measuring the minus 98 dBc per hertz we were measuring before, which is quite a bit worse than the PNCS1. So in order to appreciate why we're measuring the phase noise of this guy, we have to look at the block diagram of how the EXA actually works. But even so, how do we get better than that? So what do we do if we have a source as clean as the PNCS1 and we want to measure it? What kind of instrument do we need to be able to measure the phase noise of something so clean? So now that we know there are limitations using a spectrum analyzer to measure phase noise, we want to know how can we make it better? What kind of measurement techniques do we need to be able to measure sources which are much cleaner than the instrument we're trying to use to measure them. And of course, the reason this doesn't work very well for us right now is because we're doing basically a direct spectrum measurement method. And that means that the spectrum analyzer is going to down convert the signal we want to look at into an IF section and then digitize it. So for that, it means that the internal synthesizer of the spectrum analyzer itself would have to be very, very clean and much cleaner than the signal you're trying to measure. And that can't always happen because the spectrum analyzer has to sweep, and its synthesizer therefore is going to have some limitation in terms of how much phase noise it will have. So that's always going to be a problem. Now, there's also a carrier removal method, which I talked about a little bit earlier, that helps to eliminate the particular AM noises and gives you a much better measurement method to give you the kind of low phase noise measurements you want to do, but still that is limited ultimately by how clean the synthesizer is going to be. There's not much you can do about that. That's always going to be part of the measurement. So we have to find a way to eliminate that from our measurement. And this is where the magic of cross-correlation comes into play. Using cross-correlation techniques, we can measure the phase noise of a source far below the phase noise of the measurement instrument itself. But how can that be? Well, let's go through the block diagram of this idea and it will become clear very quickly. Let's imagine that I want to measure the phase noise of this device under test. And let's say that this is a very clean synthesizer whose phase noise is much better than the phase noise of the spectrum analyzer that I have, just like the situation we had earlier. I'm going to take that signal and I'm going to split that into two using a very simple power splitter. Now what happens is that you're going to get two signals, one over here and one over here. Now as long as these cables and the connections between these things is not longer than the coherence length of the signal itself, which can be done if everything is compact, the signal at this point and the signal at this point is identical, meaning its phase noise, its amplitude, every aspect of the signal is exactly the same. So we basically replicated it twice. And then what we have to do is we have to build two parallel spectrum analyzers. So we are doubling the entire hardware. That's how expensive this instrument is, because you're basically doubling. It's like having two spectrum analyzers next to each other, all in one box. So we have one up here and we have one down here. So why do we do that? Well, the reason is because the top spectrum analyzer is going to have its own down converter reference, and the bottom one is going to have its own down converter reference. So now we have two LO sources which are going to simultaneously down convert two identical signals. And the output of that is going to go through a phase detector mixer and ultimately is going to go to a digital PLL. And this digital PLL allows us to measure two simultaneous phase noise, one up here and one down here. So what happens is that for each of these phase noises, we are limited by the source because the DUT is so clean, which means that even though this measurement by itself is not very useful because we're basically measuring the noise of this source, and the measurement at the bottom by itself is not so useful because we're measuring the bottom source, what we can do is we can make sure that the source at the top and the source at the bottom are completely uncorrelated from each other. Meaning that we built two separate synthesizers, we use two separate references, there is no overlap between them at all, and therefore their phase noise, which is a statistical variable, is completely random and independent of each other. So the phase noise that you measure up here and the phase noise that you measure down here have only one thing in common. The part of the phase noise that's in common is the part that comes from the DUT. The part that is not in common is the part that comes from the source 1 and the source 2. So now think about this. I can make many measurements. Every time I make a measurement, I do a correlation comparison. Every time I find a correlation between the two phase noises, I keep that part. And every time there is no correlation, I throw that part away. So the part you throw away, therefore, will become the random phase noise of the top synthesizer and the bottom synthesizer, and they eventually cancel out. This process takes a long time, and you have to do hundreds or maybe even thousands of measurements to continue removing the correlated phase noise of the top and the bottom source. This is, in a way, genius and straightforward when you think about it. The challenge is, of course, you have to build all this and replicate the hardware and build all the digital PLLs and write all the functions. And the thing that becomes a little annoying with these systems is that if the instrument is not fast, it's going to take a very long time to do the correlations, and it's going to take a long time no matter what if you want to get to really low noise levels. So the nice thing is I actually have one of these instruments in the lab, so we can go ahead and see what it looks like on the inside and take a look at this block diagram. And this is the block diagram of the instrument. It actually is in two parts. There's the E5053A and the E5052B. Unfortunately,
I don't have this part, and I'm desperately looking for one to add to the system, but unfortunately we don't have that. So ignore everything on the left side. This part on the left allows this phase noise measurements to be done all the way up to 26.5 gigahertz, whereas the instrument itself is limited to 7 gigahertz, which is okay. So what happens is that we put the signal that we want to measure here, and you can see there's a power splitter here, and the signal goes out here and typically falls back, and it goes into the first down converter. At the same time, this guy splits over here, goes out and comes back, and it connects to another down converter. Now this down converter has this reference LO, and the bottom one has this reference LO. And you can see there's a line of symmetry down the middle. Everything at the top and everything at the bottom is completely independent of each other. So we're building twice as much hardware, as I said earlier. All the digital PLL stuff at the top is here, all the digital stuff at the bottom is here, and here's the cross correlation in the middle. So eventually it does many measurements in the background, and once it does it, it continues to improve the phase noise floor and continues to get better and better. This can be a pretty complex and expensive instrument as a result. So if you go back over here, we can do some calculations and find out how much phase noise improvements we can get the more we do cross correlation measurements. So here it is. You can see here's our first channel, that's the top channel, and here's the bottom one, the bottom channel, and here's the splitter like I was explaining earlier. So that's exactly the same, and here's the cross correlation. This is all done in the digital domain once everything is digitized. So you can see that if you do 10 correlation measurements, you already get a 5 dB improvement in noise. So you almost quadruple the amount of noise you can remove. If you do 10,000 correlation measurements, you get a boost of 20 dB, which is huge. It's an enormous improvement. Now 10,000 is going to take a very long time, but we can actually do this, and we can use this instrument to do this measurement just like I said. First, I want to just take the cover off and show you what's inside the unit so you can identify and see each individual component that we see here directly in the instrument, and then we can go back and do some measurements directly on. And there's lots of capabilities that E5052 has, which I think is worth exploring. So let's go ahead and take a look inside, and then we'll do some measurements.
So let's take a quick look inside this unit. I'm not going to take it completely apart. There's a lot going on. I just want to give you an overall idea of how the system is put together based on the block diagram and the principal operation that we just went through. So of course at the core we have a simple processor, Intel processor running a Windows XP operating system on there. And this is nice in some ways because you can easily upgrade it. I just upgraded the memory and then another half a gigabyte of RAM to it just in case, it needs a little bit more. And then everything else looks good. I changed, there was a problem with the fan, the battery was dead, so I replaced that. Just a few minor things here and there for repair, nothing really serious. Now if you look, here's channel 1 and channel 2 portions. This is the oven controlled crystal oscillator for one channel, this is for the other channel. Interestingly enough, they are different from different vendors, it looks like, and that might be partially because they want to decorrelate the core PLL of the two LO signals inside as much as possible. As I spoke about it, that decorrelation is really important, allows you to eliminate the phase noise of the down converters from the entire phase noise measurement. That's the whole point here. Maybe that's the reason why they've done this. And both of these are on shock absorbers, you can see, and even though this is on its side, I can move the entire structure around because this is on rubber feet, allowing it to absorb any vibration. Normally you don't have to go through this much trouble if you're making a spectrum analyzer or a synthesizer, but when you want to measure phase noise down to 1 hertz offset, you don't want any vibration, anything feeding into the core of your PLL, and that's going to throw everything off. So you want to be as quiet as possible. And this is the reason why they've done this. This is the reason why these are such large oven-controlled crystal oscillators, very high quality. I don't know what the Allen variants of these are, but I'm assuming that it's very good. A hard drive over here, some fans over here, interesting, 2 different sizes. And through here you can see that's all the RF is on the other side, and all the RF boards for both of the channels are underneath this section, power supply. Nothing really unusual. Let's flip it to the other side and see if we can identify some of the RF components that sit in the front end of this instrument before it gets into the 2 down convert modules. And here's the bottom of the unit where all the RF stuff's connected. Now, of course, these boards are all going to have all the RF magic that includes down conversion, digital RF, digital PLL, and all the other things that happen I spoke about. But the front end microwave components are present here. So the input comes over here. You can see that we go into a power splitter. And this power splitter has 2 outputs, of course, one on this side, which then splits into 2 again. And these 2 go outside of the unit and back in, and they do that so that if you have the frequency extender, you can connect it to it as I showed you. But then once they come back, they go into these 2 parallel attenuators, and the output of the attenuators go down into the unit on the other side, where the 2 down conversions happen with 2 uncorrelated local oscillator signals. Here we have the other part going in here, and we have the detection going on, so that's for the power detection and all the other things which I also showed you on the block diagram. But everything coming out of this attenuator and this attenuator, these two, are all fully correlated to within the thermal noise of the system. What is on the other side are all the uncorrelated signals. That's why everything here is so parallelized and is essentially kept so symmetrically in order to ensure that that happens. Some power supply regulation and DC-DC conversion and filter isolation potentially happening here. I/O drivers for the board to get a connection to the bus. Attenuator control is of course also on here. This is the analog section for the detector. So it looks really nice. Now the question is, what do we measure? What should I connect to this to really push its limits? And I think I have the exact thing to start with. And here's the Agilent E5052B. So we're going to use that to measure the PNCS1. I've already connected to the input. We're going to turn it on and then configure the instrument to do phase noise with cross correlation. And here's our plot over here. We're looking at the 10 Hertz offset all the way up to a 100 megahertz offset over here. And you can see the shape of the curve as to be expected. Now the numbers here are really astonishing. First of all, the correlation is running in the background. It's been running for some time at the bottom over here. And we've already done 16 averaging. So we're basically reliably looking at these measurements now. Probably the mouse is a little bit easier to use. So if you look over here at a 100 kilohertz offset, the phase noise is minus 149 dBc per hertz. This is an incredible number. This is the only instrument in the lab that can actually measure the phase noise of the PNCS1. And it of course matches the specification. Even at a 10 Hertz offset, the phase noise is minus 90, almost minus 91 dBc per hertz, which is incredible, both because the PNCS is so clean and stable, and of course because of the correlation functions and the super clean synthesizers inside the E5052B. And you can see the shape over here. I'm going to leave a puzzle for you. If you can tell me why there's a drop here. In order for you to figure out why there is a drop here and answer that question, you're going to have to go and watch the video for the PNCS1, and hopefully there will be some hints in there of why that happens. We can also do an integrated jitter in exactly the same way we did between the same two frequencies, and you can see the integrated jitter is 24 femtosecond. That's 10 times better than what the EXA was reporting. That's because we were measuring the integrated jitter of the EXA and not of the PNCS1 reference source here. This is another indication why having an instrument like this is so important, especially if you're doing PLL work. Now the 5052B is by no means the state of the art. This instrument is fairly old. Both Keysight and Roden-Schwarz and Holzworth all have better cross-correlation phase noise measurement instruments that does even better than this one. But this is still a fairly good instrument for these type of purposes. These numbers are quite incredible. At the 1 kilohertz offset, minus 136.7 dBc per hertz. Yep, it's a very, very clean source. Now the capabilities of this instrument go beyond this. Because it has a built-in DC control on power, we can actually measure VCOs directly on it. And because it has a digital PLL, we can lock the VCO directly on the instrument, making VCO design quite a bit simpler using the E5052. So let me set that up as well. So here's our VCO measurement setup, which is a little different. The VCO is directly connected to the input of the instrument from here, but the VCO control voltage is controlled by the DC control of the E5052, and the VDD of the VCO is also controlled by the DC power. Both the DC control and DC power are ultra low noise in order to not pollute the signal coming from a sensitive VCO. And of course, there's the digital PLL, which can lock this VCO and give us very precise measurements. At the same time, we always have CAT scan. He's always watching, making sure the measurements are correct. And here's the measured phase noise of the VCO. I've already asked the instrument to lock the VCO to 1.9 gigahertz, which is what it has done, and there's the phase noise response. You can see it's nothing unusual. But this is not the part I wanted to show you. What I wanted to show you is actually this measurement, which is the measurement of the VCO itself. We just have to trigger to that. There we go. So what this instrument is now doing is that it's sweeping the control voltage and measuring the VCO frequency. You can see the VCO frequency going from about 1.75 all the way to 2 gigahertz. It's also plotting the KVCO, which is quite nice, in megahertz per volt. At the same time, is plotting the output power of the VCO and the power consumption of the VCO. as a function of the control voltage. Now the power consumption of the VCO goes up just a little bit across frequency. That's kind of to be expected. It is going to be running at higher frequency with higher control voltage. At the same time, you can see the power goes up with frequency, which is unusual a little bit. And then we have, of course, the frequency. So this digital PLL built into an instrument like this allows for these really good measurements. You wouldn't normally be able to do this with a spectrum analyzer because you wouldn't have a PLL locking the VCO. So all the drift of the VCO would be very hard to capture. But this, by locking the VCO to a digital PLL, eliminates all of that, making VCO measurements quite a bit easier. So we talked so much about phase noise and how to measure it and what kind of instruments are used to measure it, but we didn't really talk about what happens to communication systems as a result of phase noise. So phase noise pretty much degrades the performance of any system, radar system, optical system, wireless or wireline system. So of course each of those is a very interesting topic, but here I'm just showing you one example. So here we have a 64 QAM constellation at a carrier of 2 gigahertz. This is about 25 megasymbols per second. So you can see the constellation is fairly clean, and the EVM is very good, and the SNR is very high. There's occasionally you see some dots appearing in the middle of the constellation. It's because my clock references are unlocked. This is across the lab. But nonetheless, this demonstrates the point. So right now, the phase noise of the system is very good. So you can see there's absolutely no degradation on each of the constellation points. They're all basically as small as they can be, considering how they're viewed on the screen. So what I'm going to do is I'm going to add phase noise on purpose to the carrier. Now, and the phase noise that I'm going to add to the carrier is going to degrade the performance of this constellation. But we can kind of predict what would happen. A phase noise is a phase deviation of these points with respect to the axis. So it's a vector. So basically the vector is not completely steady. If I add phase noise, the vector will move back and forth like this, which means that the outer points of the constellation will suffer much more than the inner points. So if I were to add phase noise, we should be able to see degradation of the outer points of this constellation be much more affected and smeared across the screen. So let's go ahead and add that. Okay, let's go ahead and add some phase noise. And here we are. There it is, and check it out. As you can see, exactly what we were expecting is happening. The outer points of the constellation are smeared across the phase domain, while the inner points not so much. And that's because we are basically having the phases jiggle around, and every time you sample, you're going to get a different point on the constellation. So this can be a major problem because, as you can see, now there is a certain ambiguity assigned with each of these points. And eventually, if the phase noise is bad enough, and I can continue to increase it, it can become so bad that this receiver will not be able to discern the points anymore and start getting totally confused. Here it is. You can see every once in a while this receiver is losing the lock on the constellation, and the points are no longer distinguished from each other. This can completely ruin the bit error rate of a particular communication network here. So this is one of the reasons. Now remember, this has no noise in it. This is purely phase noise. If I were to add noise to it, the points would not smear across the screen, but rather they would get larger. That's a signal to noise ratio problem, a totally different phenomenon that I will cover in the noise figure tutorial that I'm going to do in the future. But for now, you can clearly see the impact of phase noise on the constellation. And there you have it. I hope you enjoyed this video. Lots of information in it, and of course you can write books on these, and people have, and we just really barely scratched the surface because there's so much stuff happening in the background that I just skimmed over, and hopefully this would be a good pointer for you to go and read more about it. I want to thank my Patreon supporters. It would be impossible to make these videos without your support, because just the components to buy and show these demonstrations already cost much more than the level of the Patreon support I have now. So this, as you can imagine, is very helpful to be able to continue doing things like this. Either way, I'm grateful that you guys are watching. I'll see you next time.